Welcome, everybody. We'll get started in several minutes. Thanks for taking time out of your busy day. We have a really cool webinar today. Semaphore and their Labbit system are doing some game-changing things, so it'll be really interesting to see all the things they're doing. We still have people joining, so I'll just give it another 30 seconds here. All right. Welcome, everybody. Today, our guest is Semaphore Solutions, and they'll be talking about their next generation LIMS environment solution called Labbit. The title today is AI Readiness in the Lab, How Knowledge Graphs Unlock the Future of Scientific Data. And we will have two speakers, Megan Bowman and Paul Saunders. So today's agenda, we'll just do our quick rules of engagement. We'll give a brief industry perspective, and then I'll introduce Megan and Paul, and they'll give their talk, and then we'll have a Q&A at the end. If for some reason we don't get everybody's questions answered, we will follow up with everyone and post the answers. So put your questions or comments in the Q&A or chat box, and there's two areas you can do this. The Q&A box, you'll be anonymous, and the chat box, people will see your name when you're asking questions. So just be aware of that. If you have to leave early for some reason, please just put your questions in there and you can come back and watch the recording. Yes, it will be recorded and will go on demand. We'll try to address all questions. If there's any very technical questions, we may have an expert answer those, and then again we'll send that out to everybody to see the answers for that. So 2015 Visioneers, it's been around 5 years now, and we are also consultants in the space. And we'll just give our little bit of our industry perspective before Megan and Paul give their talk. So model quality data has gone from an evangelism to an imperative. The real goal here in life sciences, material sciences, agri-sciences is to have reproducible, contextualized or contextual and machine actionable scientific data. In other words, it needs to be model quality data. And the reason for this is 25 years ago, we were just starting to do machine learning and life sciences, and we were getting some awesome results and stuff, and has exploded since then with the use of AI. And AI needs good fuel, it needs model quality data. So how do you get that? When you deploy systems and solutions in your lab, you have to have that detail of what you're doing and how you're doing it. And we use business process modeling to do that. And you're going to hear more about this today. We want to make sure the metadata is there, it's contextualized, and the details are there. And then the stewardship. In today's world, data is an asset, and everybody is a steward of data. So you need to put in some rigor. Even in research, you need to put in some rigor so that you have and produce reproducible experimentation, reproducible science, reproducible testing. And it's really not negotiable anymore. It can't be, oh, we don't need to do that. We don't want to do that, because the problem is your data is not just for you, but it's for everyone in the organization. And especially now with AI and large language models, that data is all being pulled in to help people make better decisions, get faster insights, and really improve efficiency. And if you just look at the beginning of AI today and how fast it's changed and how it's continually getting better, it's amazing. So, and there, scientific intuition and reproducibility collapse without structured context. We've built the maps. AI is just learning how to drive now. I'm just reinforcing what I just said. It's in its infancy, but its infancy has grown up very quickly. So you have to realize that you need this process intelligence to produce fair data. So having a digital process backbone, having those BPMs done, workflows, they ensure compliance and automation, that metadata contextualization, the advanced scientific data environments with AI and large language models, digital twins. So you need fair. You need not just fair data, but you need fair processes, fair instrumentation, fair lab operations to make this all work. So findable, accessible, interoperable, and reusable. So I'd like to introduce Megan Bowman. She's the Senior Product Manager at Semaphore Solutions. She's a seasoned product manager with over 10 years of experience delivering SaaS and LIMS solutions across life sciences, healthcare, and agriculture. At Semaphore Solutions, she leads software development for modern labs in clinical diagnostics, R&D, and quality control. Megan specializes in streamlining lab operations and data workflows in a regulated environment with work spanning pharma, global agriculture, and animal health. She holds a BS in biology from Salve Regina University and is based in Connecticut. Paul Saunders is VP of Sales and Marketing at Semaphore Solutions. He has over 25 years of diverse experience in software, healthcare, and life sciences. As VP of Sales and Marketing at Semaphore, he drives commercial strategy for AI-powered lab software across molecular, biopharma, and manufacturing sectors. He has led growth at companies like One Health, UMethod Health, and Origin Labs, with a focus on precision medicine and genomic testing. He's previously held senior roles at LipoScience, Abbott, Medtronic, and Boston Scientific. He holds a BA in economics from UNC Chapel Hill and has completed executive programs at Duke, Kellogg, and Babson. And with that, I'd like to turn it over to Paul and Megan.
All right, thank you, John. I'm going to share, if I could. Then I'm going to pull this over and get it out of the way. So making sure you guys can see the slide deck.
Yep.
Okay, perfect. So thank you, John, for that introduction. We certainly look forward to presenting to your audience today and are anxious to really talk about both the Labbit system, but first of all, talk about data quality, talk about knowledge graph, talk about infrastructure. So I'm going to turn it over to Megan to kick us off, and then we'll go from there.
Great, thanks, Paul. You can advance the slide. Great, thanks. And thanks, John, for the introduction. Very excited to be here today. So today, to frame today's discussion, let's start with where things are heading. Paul, you can advance the slide. So AI is already reshaping how labs manage, but also interact with their data. Natural language is becoming the new interface, simplifying data exploration and interpretation. This shift is creating new possibility across the entire lab ecosystem. At the same time, we're seeing that data literacy is becoming more important, not only for specialists, but also for data consumers. Understanding how to work with AI tools, validate the results that are produced from them, and also ask the right questions is integral to gaining true value from them. As these technologies evolve, there's growing recognition that labs will benefit from informatics systems that are flexible, connected, and built to support this shift. Informatics platforms that can manage complex relationships, scale with data complexity, and evolve alongside scientific innovation are better equipped for what's coming. So, with that in mind, let's take a look at the current adoption landscape, as well as some of the primary challenges facing labs as they navigate this journey. Next slide, thanks. So let's start with where we are today in terms of adoption. This data from Gartner shows how different industries are approaching generative AI. As you can see, life sciences is in the middle of a major shift. As of 2024, nearly half of organizations in this space indicated that they planned to deploy generative AI within the next 12 months. Now, we are halfway into 2025, just about. We would anticipate that these efforts are well underway, but may still be early in process. So now is the time to ensure the right data and infrastructure foundations are in place to support this shift. As generative AI moves from pilot to production in lab environments, it will demand much more from the systems behind the scenes: more structure, more interoperability, more context in the data it's learning from. Establishing the right infrastructure early can really help organizations better support their AI adoption. So let's look at some ways that we're seeing this evolve within the laboratories. AI is reshaping how we approach research, diagnostics, and drug development in fields like molecular genomics and early stage drug discovery, where data is generated rapidly and in large volumes. AI helps uncover patterns far faster than manual methods. Beyond just analysis, though, AI is also optimizing experimental design. With predictive modeling and simulation, scientists can anticipate outcomes, refine hypotheses before even running an assay, saving time, reducing cost, and conserving resources. We're also seeing increased adoption of automation. AI-powered systems are streamlining repetitive tasks, freeing up skilled scientists to focus more on critical thinking and innovation. These advancements are boosting efficiency, quality, and the pace of discovery, but they also highlight a crucial point. AI is only as effective as the data it's learning from. Today, we're going to look at some of those key data challenges labs are facing and explore how to better prepare data for meaningful AI-ready consumption. So, looking at a few of the barriers facing labs today as they look to adopt AI. First, data fragmentation across systems. Lab data often lives in disconnected locations. This is inclusive, but definitely not limited to ELNs, LIMS, spreadsheets, other software, and other systems. Each of these sources may have a different format and structure to the data, making it challenging to have a completely unified view of the data that you're looking to ready for AI. Second, unstructured data. A lot of valuable lab information, such as experiment notes, image annotations, custom observations, may be stored as unstructured data, posing a challenge for AI models to extract insight unless it's further contextualized in a meaningful way. Third, lack of standardized terminology. Different teams, or in some cases, even individuals, may identify objects, attributes, or labels differently, posing a challenge to make reliable connections within the data or learn patterns across these data sets. And finally, there is the challenge of infrastructure scalability. Many lab systems were not originally designed with AI in mind, which can make it difficult to support the dynamic relationships that emerge, rich metadata, and the evolving data models that AI thrives on. Now that we've discussed the current landscape of AI adoption, as well as gone into some of these key challenges, which we will revisit throughout the presentation, I'm going to turn this back to Paul, who will be providing some context around what actually constitutes AI-ready data.
Great. Thank you, Megan. So the question in the framework is what makes AI ready data, right? So I want to dive into a little bit and thinking about a little bit about this framework. When we think about data management, right, more specifically about the quality of data, that's really a heart of our conversation is the quality of data. I ran across this quote from Gartner, which states 30% of AI products will be abandoned after proof of concept due to poor quality data. So part of this conversation is really about to ask ourselves, why is this, or how can we prevent failure and ensure good quality data in the implications of AI projects? Okay, so let's dig into it a little bit. As we look to discuss the data framework or infrastructure, we have to think about quality, consistency, and relevance over mere volume, right? So that's maybe a strange concept, but data, volume isn't of value. The potential of it is, but we really, as we navigate the era of exponentially growing data volumes, the focus must shift from mere accumulation to actionable impact. In other words, scientific decisions, laboratory trends, integration with post-analytical tools all depend on one thing: data that is accurate, it's relevant, and ready for insight, right? So when we talk about data framework or infrastructure, we're not just referring to the storage or pipelines. We're talking about the foundations of quality, consistency, contextual relevance, as John alluded to. It's not how much data we have, but it's how much is usable, trustworthy, and ready for analysis from an AI tool, right? As I mentioned, raw data holds no immediate value in some sense. As it states here, data is the fuel. It must be refined, it must be processed and transformed into something meaningful. Its true value lies not in its existence, but in the potential to drive decisions. Yet most organizations are far from realizing this potential, right? According to Gartner, only 4% of organizations report that their data is AI ready. That means a staggering 96% are struggling with fragmented, inconsistent, low quality data that impedes innovation and insight. So continuing on with that theme, the data infrastructure challenge. So it's broken down in 3 or 4 areas here. Today's labs are sitting on a gold mine of data. We know that, and that volume is increasing daily. But harnessing its full potential remains a major challenge, right? 40% of organizations cite the lack of interconnected data as a key obstacle. So let's think about that, right? We really got to make sure our data is connected, and we'll talk further about that in the presentation. Many struggle with the basic question: how do I gain access to the right data at the right time? Complicating things further, only 30% of data is structured. So while the other 70% is unstructured, like images, text documents, and sensory logs, the biggest challenge we face is organizing the unstructured data, aligning it with structured sources, making it usable for AI. And so when we think about this, and it now matters more than ever, right? In this fast moving, if you will, AI environment we live in, 75% of the organizations say that AI ready data is top priority. But are they really prepared? Are you prepared to really think about this challenge ahead of you? So how do you ensure that your lab's infrastructure is fully ready to take advantage of AI tools? So let's explore simple models to help us access and prepare your lab for AI-powered future. So when we think about capturing the data, we have to think about the framework before we think about the AI-ready data and the usage of that data. If we look at this diagram, the AI-ready data in the diagram is at the core of the structure or the goal. So let's think about what's around this goal. On the left side of this diagram, we'll think about the alignment or relationships of data and metadata. The data can be internal or external to your lab. It can be clinical trial data. It can be white papers. It can be testing data. So let's dive a little bit into the metadata itself, right? So metadata essentially is the data about data. Might sound crazy, right? It describes the characteristics, the origin, the usage, and the structure of data assets. So let's talk about a few examples just to ground this a little bit. Technical metadata might be table names, data types, schema, column definitions. Business metadata might be definitions, ownership, policies. Operational metadata might include data lineage, pipeline logs, or data freshness. How often is that data coming in? And then usage metadata: who accessed the data, how often, from where, right? So why does this really matter? Well, let's think about a few concepts here. Data discovery, right? Make it easier for users to find the right data and find it quickly through catalogs or search or other means. Data governance or compliance helps track data lineage, access controls, regulatory requirements, depending on whether you're what environment. It could be HIPAA, it could be GDPR, it could be other things that we need to make sure that our data is around. How about trust and understanding? Provide context to help users understand what the data means, where it comes from, and how it's used properly. Impact analysis. Identify downstream dependencies on this data, the data sources and the schema and the changes that when they occur. And last but not least is enabling AI, right? Well-managed metadata is the key to automated data profiling, feature discovery, and model transparency. So it does truly matter. So on the right, let's shift gears a little bit and go to data observability. Think of data observability as the monitoring, the diagnostics, and alerting system for your data pipelines. It's like a data ops control tower, if you will. It tells you when something is off before your stakeholders notice. Key components of data observability. Number one, data freshness. Are your data sets up to date? Are they arriving as expected? Data quality. Are there missing, null, or out of range values? Are formats consistent? Data lineage. Where did the data originate? How has it transformed over time? Data volume and distribution. Are row counts, distribution, schema changes anomalous? Could they point to critical insights? Labs unprepared for AI often treat anomalous data as noise rather than a signal. It could create a blind spot in the data. Has there been a sudden spike or drop in your volume of data? And what insights could it offer us? Systems and pipeline health. Are your jobs running on time? Are they not? Where are the bottlenecks? What's occurring? So why does it matter with respect to data observability? It allows you to detect issues early before they affect downstream tools like dashboards or data models or scientific reports. Increase trust in data products and insights. Improve root cause analysis when things break down. And it also enables better communication between data engineering, analytics, and business teams. Are there bottlenecks? Are there failures in the business? Do we need to make changes? So it does matter to each and every one of us. And third, kind of the third leg of the stool here is the governance at the bottom here, right? So DA governance, textuality, if you will, textually points to the idea that data analytics governance should not be rigid. One size should not fit all. Instead, it means to contextualize, meaning it takes into account the specific business needs, desired outcomes. This means tailoring governance policies and practices based on factors like business goals and objectives, industry regulations, data sensitivity, right? Perspective sensitive data like personal information, data usage. How is data collected, stored, processed, and shared? Stakeholder needs, ensuring that the data governance is relevant and effective for all parties involved. So why is it important again? In real world terms, improve decision-making by understanding the context of your data. You can drive deeper insights and make more informed decisions. And at the end of the day, that's really what we're after. Enhance compliance, right? Tailoring governance to specific regulations helps ensure compliance and avoid penalties. Increased efficiency. Contextual governance avoids over-governing data that doesn't require it, reducing bottlenecks, promoting efficiency. And last but not least is innovation. A deep understanding of data context can help identify new opportunities for growth, innovation, and keeping up with the science. So let's get a little bit into the knowledge graph itself, right? John talked a little bit about knowledge graph and the way Labbit kind of utilizes knowledge graph. We're one of those unique limbs that sits on top of a knowledge graph, but we believe those are the right decisions made a year ago. So let's explore the framework of knowledge graph in the database, right? So in its simplest terms, what is a knowledge graph? So to remind everyone, it's a structured representation of information, and it captures the relationships between entities, such as people, places, events, or concepts in the form of a graph. So there are three concepts around knowledge graph. There are nodes, edges, and labels and property, right? So nodes represent entities or concepts, right? So The Labbit system is entity-based. It's not sample-based, which in simple terms means we can track anything and everything that we want to within a knowledge graph setting. The edges represent the relationships between those entities. And then labels and properties, they provide additional context and semantics to both nodes and edges. In other words, it just allows this, if you will, this ecosystem of information and the inferences between those information to be really understood well. So the key characteristics around which Megan will talk a little bit about is you have semantics, which is the encodes the meaning through ontologies. We're going to spend some time talking about that. Interlinked, right, enables connections across diverse data sets. And machine readable, as John referred to, designed to interpret and used by algorithms for tasks of search, recommendations, or reasoning of the data itself. So in simplest terms, the common use of this is search engines. If everybody didn't know, Google is probably the biggest well-known knowledge graph out there. And so it takes to enhance the results with rich contextual information. So think about a knowledge graph pulled back into the life sciences sector, or think about it in your own lab setting. You're now going to have your own small Google, if you will, able to both internal data as well as external data, but get this contextual information if you have about the topic or study or experiment that you're doing. So it certainly lends itself to, well, I think I reach out to Google probably a dozen or more times a day, right? It also is used for recommending systems to understand user preferences, right? It's also used for question, answer, or AI assistance, especially in the day of term we see AI. You'll see a lot of new AI assistants or other things that think up assistants along the way or ask it questions or lend support to us as we look to our experiments in other ways, right? So connected and captured in the right way, what does it really mean? There are four things, and John, you touched on this a bit, four primary functions of a knowledge graph. Storage of fair data, right? Findable, accessible, interoperable, and reusable data. So storage of fair data and metadata in its context in the form of data and metadata and those relationships. It has the ability to naturally model complex real-world relationships and workflows. It's going to bring it down into the lab's world and make sure that we model it around all those entities and relationships and data that you want to capture. It has the auditability and provenance of the captured data, right? This is the trust, if you will, part of making sure that the data is captured in the right way, that we have audit trails, we have provenance, the who, where, and how it occurred, when it occurred, and have those even under FDA guidance or other aspects of it, we have that provenance that we can go back and trust and ensure that we're getting the right data in the right way. And then easy to reuse and search, right? We've got to make it easy to use. In other words, we've got to stay out of the coding or of this. We've got to use natural language. We've got to make the user interface easy for you to be effective, right? Allow you to focus on the science, also to be able to look at trends, but to make this an easy access. We don't necessarily want to introduce something to the world of these labs and making sure that it's difficult to use. We want to make sure that you, the end user, find it very simple, intuitive, and easy to use. Okay, so let's jump in a little bit more to the fair data principles. The first one of that is in fair is the findable, right? Just to review, John did a good job of this, but I wanted to spend a few minutes of thinking about the data needs. The data needs to be connected. So our analysis is true to all the sources of data needed, both internal and external data, making sure it's connected, make sure it's findable, right? Make sure it's accessible. And if we can find it, then making sure the next thing is how do we access it? If we can find the data and we know it's there, it's true, then make sure it's accessible. Locate, find, and share the data to the appropriate analysis or applied AI resource, right? And also, again, as I said, it needs to be user-friendly and retrievable in that respect. On the other two in the acronym there, FAIR, is interoperable, right? Integrate data from different resources in its analysis, applying results from different experiments without risk of errors, right? This allows a scientist to arrive at a quicker conclusion, accelerate product to market, or just gain insight on an experiment to make a decision point. Data sets can easily be combined without the risk of error if it's done in a proper way, right? If we're trusting the data, then we get back to the real science of what we're trying to, or the decision points we're trying to make, all right? And is it reusable, right? Maximizing value. Data sets are properly documented. They're collected with rich contextualized metadata. By embracing these FAIR principles, if you will, harnessing the power of AI technologies, laboratories can unlock the full potential of their data and accelerate discovery and delivery to the marketplace. Okay, so I wanted to backtrack just a bit. John also mentioned this business process mapping. And so there are multiple ways you can capture data and metadata, right? One of the most effective is through a business process map or a workflow visualization tool, right? This helps clearly outline and understand how data flows through a system, right? As an example, this is one of Labbit's, if you will, BPMN or business process mapping and notation tools. We use a tool called Communda, which helps us kind of think about these when we talk to clients, which functions, it's similar to that of like a lucid chart diagram, right? It visually represents each step in the process from the moment of a sample arrives at the lab to where the results are generated, right? This mapping allows you to understand each step and decision point. So we have circles, arrows, both some highlighted, some non-highlighted, right? It identifies the data and the tasks required to move to the next step. So we know what was done, when it was done, and by whom it was done. So if you can see this, we take those communda, if you will, models, and we inject it right into the Labbit system. So you're both be able to see this visual tool, right? And you'll be able to map out when and what data, who's doing what task, and making sure that we understand what the process flow of that data. Each box represents a task that's being done. So we have both a box, we have a workflow, and we have a workbook or a task associated with that. We understand what data is being captured in each one of those. Well, whether we can also put in tools, quality assurance tools. We can put regulatory compliance steps in there if it's FDA, 21 CFR Part 11, making sure that electronic signatures and audit trails are present. It simply gives you if you will, a guidepost or a visual guidepost to understand each one of those steps is where we're injecting data into the knowledge graph, right? So the provenance of that data is being pushed in there. And we're allowed to go down and look at each step along that way. And if bottlenecks occur or if other things occur, you also have version control. You have the ability to go in, make changes to it, understand when that change was done, by whom that change was done, and what workflow it was done under, and how the results might have changed. So it's easy enough to have, there's a lot of discussion points around being able to change workflows. What do you do to change it? What version are you on when you look at those changes? You have a system like this, which has provenance to every one of those steps and making sure that we have all that captured for an audit trail or anybody else who wants to come in and look at an experiment prior to a change and then post change. So on the left there is just one of the highlighted boxes there. You'll see it's a nested workflow with more detail. So you can get down to each step within the step in making sure you're capturing the right thing. On the right there is just an example of a location management or storage management, one of the tasks that might be created within one of those workflow steps. So I just wanted to ground everybody in that. So there's a lot of tools to do that, but this is one of the major ones where you get pictures worth 1,000 words, if you will. You get to see it, understand where your samples are, how they're moving through the system, and then what data is being captured in each step. So in summary, just kind of looking at a knowledge graph, right? So we understand we're looking at relationships between entities, right? People, places, products, process, concepts in a graph format, right? It's designed to mimic the way humans think about and connect knowledge. That's why, hence the name knowledge graph, right? It enables smarter research, recommendations, reasoning, decision making, right? So again, as I said, we have these entities, right? Real world objects like person, drug, experiment, gene, data sets. We have the edges, which are the relationships, right? How those entities are interconnected, right? Then we have the semantic meaning, if you will. A graph carries context, not just connections, right? It's powered by ontologies, taxonomies, and metadata, which Megan's going to spend a few minutes on. But then you also have the schema flexibility. Unlike some of the relational databases out there, knowledge graphs are schema light or schema-less, which makes them ideal for evolving interconnected data. So in this market, especially today, as everything is evolving and changing really quickly, knowledge graphs brings that in and allows you to kind of look at this and not be so structured and allow you to understand those relationships in data when you're looking to design experiments or looking for data insights, right? Why use a knowledge graph? Well, I think here, contextually, search and discovery, find data about something, not just matching keywords. Better data integrations, right? So we can easily unify from different sources and formats. Improve analysis, right? It's moving very fast these days. Identify hidden patterns, correlations, insights. AI and machine learning enablement, right? power reasoning, we're thinking about natural language interfaces. It's easy to think about knowledge graph and then make it easier to use their interface to arrive at those conclusions, right? And then regulatory and scientific traceability, right? Trace how data relates across processes, people, and systems. You can see here, as we think about that unstructured data that's sitting out there and the way that it can pull that together and design it, it's a data fabric network. I love the third one down. It's a data fabric network, right? So we're a multi-layer connected network of internal and external data points. Those can be experiments, those can be clinical trial data, those could be even white papers and somebody who's done research on that, right? And then it delivers you an AI-ready data in the right way, right? The quality, the governance, the structure, the unbiased, ready to deploy, if you will, to other tools. There's a lot of AI tools coming out there, or you have your own BI tool. It's easy to connect it in as you start to move forward and think about your business. Okay, so core concepts, just to review real quickly. As we think about this, natural model of relationships, right? In other words, we have an experiment, we have a sample, we have an instrument, we have scientists, we have protocols, we have results, we have what reagents were used, right? What regulatory governing are we looking for compliance under 21 CFR Part 11? So it allows you to think about those entities and the relationship. As I said, it's entity centric, and so is Labbit. So it has these built-in relationships of whatever you can think about tracking, the system will grab that, and the knowledge graph will grab that as well and establish that relationship between those. As you think about some of the edges, if you will, as you take a step further, and I don't want to complicate this too much, but if you think about the edges of a knowledge graph, it thinks about the experiment, it thinks about the uses, it thinks about the protocols, right? It's establishing this relationship, or it's thinking about the experiment. Who was it conducted by? Who was the scientist that did that? And when did they do that? Or we can go back to simple looking at a sample, right? It was processed in this instrument, right? That was derived from this reagent. The result was generated from this experiment. The result was documented in regulatory document this from a quality standpoint, right? Or the protocol was governed by these compliance rules. It's going to establish those edges and associate those with those entities, right? What can we do with it? Pretty simple. We can sit here and look at traceability, right? Instantly see where a result comes from, who ran it, which reagent and instrument it was performed on. Compliance monitoring, identify which protocols are tied to regulatory rules, which scientists are working under them. And then impact analysis, right? If a reagent was recalled, trace all samples and experiments it affected. Or smarter search, right? Find all experiments using a specific reagent or protocol conducted under GLP practices, right? So there's a lot of examples of it. I think if you're not familiar with the knowledge graph, it offers us a tremendous amount of data and good quality data, as we talked about in the very beginning. And pulling that data together allows you to advance your business on a level that you've never had before. So as I get to the final slide, just talking about good quality data, I wanted to talk a little bit about the knowledge graph and the structural architecture around a knowledge graph, right? It was intentionally designed to support this transformation and help labs move confidently toward an AI-driven innovation. The Labbit Lemma was developed back in 2019, or conceptually when we came up with this. We thought about the goal of taking advantage of multiple lab sources, the scientific community, and allowing data and insights to keep up with the speed of science today, right? Give you an effective way to really design and look at this good quality data and make good quality decisions. In addition to that, utilize the BPM to capture the metadata directly to the graph, right? So the data capture mechanisms, as we saw, was the BPM in workflow design, both from either a protocol, an SOP perspective, or that visual design. You can do it in many different ways, but that's delivering, the knowledge graph is going to automatically set up the foundation for your data model, right? And then it's going to allow you to build or apply AI tools on top of it, right? Then it allows you to apply the knowledge and the technology, which allows your team to work on the most efficient way to deliver recommendations, to conclusions, to new discoveries, or simply just use it as a search to gather more data, right? So part of this is getting to the top line, which is applications, right? The recommendations, the discovery, the search. AI is moving really fast these days, but the knowledge graph is a perfect foundation to make sure we have good quality, to make sure that we're moving in the right directions, and that it's going to accept today and as well as future tools with AI components. So now I'm going to pass it back to Megan to discuss how you map your data or define data relationships within the knowledge graph. Megan?
Thanks. I was talking on mute. Yes, thanks, Paul. So Paul talked a lot about the contextualization of the knowledge graph. So we're going to delve into a little more detail on how is that contextualization being set within a knowledge graph database. And a lot of this is done through the use of ontologies. And so at a high level, an ontology really acts like a map for your data, where it's defining the core concepts or entity types and outlining how they relate to each other. So in a graph, this becomes the semantic layer that's adding that context, making the data understandable, not only to humans, but also to machines. Paul talked a lot about nodes and edges, and so that really comprises your graph database. And so while you don't technically need an ontology within a graph database, it does add this significant value. Ontologies are what's helping standardize the terminology, enrich your queries, and most importantly, make your data machine interpretable, enabling those AI systems to reason with your data, not just retrieve it. So here, this example is showing references to a life sciences ontology. This is actually in one of the ontology editor softwares. And it's modeling how genes, proteins, and tissues interact with each other, making it possible for someone to explore more complex questions that span multiple relationships as a result of clearly defined terminology and relationship. So if we look at a little bit closer what constitutes an ontology, so over here on the left, we see the core components. So concepts are the main categories or entities such as sample, protocol, instrument, which appear as nodes within the graph. Relations define how those concepts interact with each other. So Paul talked a little bit about that. But then we also have properties, and this is where we're capturing attributes such as sample volume, instrument model number. Those are just a couple of examples. And then axioms are rules or constraints, such as requiring each test to produce a result or limiting certain values. So these are all components that make up the overarching ontology. Well, ontology definition should be a collaborative initiative with domain experts providing their insight around the definition of the domain, data architects and engineers structuring the ontology, and data stewards to ensure consistency and governance of the ontologies. Ontologies can be built using editing or modeling tools by embedding directly into a modeling environment or defined through simple config files. This is really going to depend on the complexity of the domain, but also the data framework that is reflecting. Once created, they're typically maintained in graph platforms or shared repositories. They're defined at various places within the data lifecycle. Some examples of this would be designing new systems or data models, integrating systems during a digital transformation, preparing data for AI or advanced analytics, or aligning with having an initiative to really align with fair data principles or regulatory standards. So as mentioned previously, ontologies are not required for use in a graph database. However, when you're preparing that data for AI readiness, interoperability, or complex analytics, they can really add significant value. Here's just a couple of the key benefits that they do bring. First, they support interoperability between systems and teams by establishing a shared vocabulary and structure. We talked a little bit upfront during some of the challenges that are facing labs, and we talked about how there can be inconsistent vocabulary. This is one approach to really aligning that vocabulary, ensuring that everyone, whether upstream, downstream, or in a different function, or even a machine, can interpret the data consistently. Second, ontologies make your data AI ready and machine readable. So in addition to being connected, AI systems need to understand the meaning of those connections. Ontologies provide the structure and semantics that models then can easily reason with. They also help reveal hidden insights that you wouldn't necessarily find in a disconnected or flat data set. Because they're explicitly modeling relationships, you can then probe and ask deeper questions that uncover patterns. They enable rich structured queries With a well-defined ontology, you can traverse multi-hop relationships across related data and get precise results. So looking at not just a directly associated entity or data, but a association of an association of an association. And finally, ontologies enforce data governance and provenance. By clearly defining what each element means and how it should relate to others, you get better control over how that data is used, reused, and trusted across your organization. So while they're not mandatory, ontologies really help make your data smarter, more connected, and more actionable, especially if you're looking to move towards AI readiness. So we can walk through what it actually takes to define an ontology. Before we do, I do want to just set some context here. What we're about to cover, this is more of a strategy that organizations might follow if they're undertaking a larger initiative, such as unifying fragmented systems, building a centralized data model, or preparing their entire data ecosystem for AI. This isn't something every lab or team needs to take on manually. In fact, platforms like Labbit come with these domain-specific ontologies already built in. So the foundational work that is described here in this strategy has already been done. And as we see later, it evolves naturally as more of your data and workflows live inside the platform. Still, for those designing their own ontologies, this is a practical way to approach it. Start off with really defining what is the scope of your ontology going to cover and the domain that it'll be for. This should consider questions such as what problems are you trying to solve? What types of data or questions should it support? It's really important to set clear objectives and boundaries to keep the effort focused and bring in the right stakeholders early. One of the best practices I do hear often from thought leaders is really starting small and building from there, rather than trying to tackle everything all at once. Identify the core concepts and relationships. So this goes back to some of that definition, working with a subject expert. What are the key entities and how do they interact? This really becomes the backbone of your ontology. An important step would also be to consult existing standards. There's a lot of publicly available standard ontologies, such as in the sources listed on the screen there. You don't have to necessarily reinvent the wheel. There's many communities that offer some of these that can then be shared, and you can leverage them, speeding up some of this definition. From there, you would import and integrate using the tools that you might have within your organization for editing ontologies or modeling ontologies. And these can then, within those tools, be overlapped with any internal structures that you might have already in place, where you can then resolve those overlaps. And most importantly, test with real data. This is critical. Applying your ontology to real lab data will reveal gaps, inconsistencies, or areas to refine. So one way to do this, you can run example queries, stress test the relationships, ensure that it's really behaving as you would expect in practice. And this is an iterative process too. So you test it and then you're going to refine your ontology and then retest. So again, if you're using a platform like Labbit, much of this is already taken care of. You inherit a ready-to-use framework for lab informatics while still having the flexibility to tailor it to your evolving domain. And just to give a little more detail on that, Labbit includes W3 provenance and core domain-aligned ontologies that reflect common life sciences and lab informatics concepts. These provide immediate structure and meaning to the data that's being captured within Labbit without requiring labs to have to build that framework from scratch. At the same time, we recognize that there may be diversity between laboratories in the processes, terminology, and evolving scientific questions that they're asking. That's why Labbit also supports custom ontologies that can grow and adapt over time, whether that means introducing new entity types, refining some of those relationships, or aligning with your business needs. What's powerful is that the more data and workflows that you bring into Labbit, the more connected and encompassing that ontology becomes. So if part of your AI or digital transformation journey involves making lab informatics data more structured, connected, and machine readable, Labbit can help you get there by embedding this ontology management directly into the platform experience. Up next, we'll quickly explore how Labbit's foundation on a native graph database takes us even further and why that architecture is such a powerful differentiator in the LIM space. All right, so we're gonna quickly jump in here. So how does Labbit help drive AI readiness and adoption? So I'd like to quote an excerpt from our vision. Labbit is catalyzing digital transformation, unlocking the value of data, and readying labs for the future of scientific innovation. This is more than just a marketing statement. It's from our core vision that shaped our product from the beginning. Labbit wasn't adapted for AI later. It was built directly on a graph database in anticipation of the current lab landscape heading in this direction, one where data would become more abundant, complex, interconnected, and critical to decision making. So for that reason, Labbit was architected in this way to be able to represent complex relationships, evolve with change, not constrain it, and support AI and automation without having to retrofit or replatform. This foundation, actually, if we go back to those challenges from the beginning, we see that this foundation directly addresses the challenges that we looked at earlier: fragmentation, unstructured data, and infrastructure limitations. So just to delve into some of those quickly, revisiting some of those key challenges we explored at the beginning and how Labbit can directly address some of them, starting with connecting siloed data. Labbit is uniquely designed to bring together diverse data sources. So as Paul demonstrated earlier in the presentation, our integrated BPMN workflow engine allows you to model entire lab processes, which can connect instruments, external systems, even manual steps. So with each of those processes feeding in and each task within those processes, it's generating data that flows into a centralized graph database where we have that contextualized data. This is eliminating silos, making that data accessible and meaningful. Since the workflows are also highly configurable from the system's perspective, you can bring more of your operational process under a single system. And so in this way, because that data is then feeding into that unified graph database, you're ensuring that all of that data is really connected. Next, handling unstructured data. So because Labbit sits on the graph database, it can handle both structured and unstructured data naturally. Whether it's free text observations, metadata, or loosely defined experiment results, Labbit flexibly models and captures these data points without having to force them into rigid tables. It also preserves the context and relationships between them, which is crucial for making them AI ready. I'm going to skip over the next one. We talked a bit about ontologies in the previous section because I do want to make sure I have time to cover the last one. Scalability of infrastructure. So Labbit's Graph Foundation is really designed intentionally for change. So it's supporting dynamic data models that can change complex relationships and volumes of data while still remaining performant. This makes it ideal for labs that are preparing for long-term demands of AI, automation, and integrated data ecosystems. So together, these capabilities form a cohesive solution to the foundational challenges facing labs on their path to AI readiness. And they reflect our original vision, a platform built for the future of scientific innovation. So some of the primary scenarios where our customers are recognizing value from the graph database today. The first area is in direct exploration of their data using Sparkle, which is the native query language for graph database. Unlike traditional systems that retrieve data from relational tables, Sparkle allows users to write queries that explore the relationships between entities, not just the data points themselves. And this is what we were talking about earlier. It supports that deep multi-hop traversal, meaning you can query those associations of associations of associations. For example, asking questions such as which experiment produced results linked to samples that originated from a specific reagent batch. So that's a question that would cross multiple entities and relationship layers, something that can be challenging to get to efficiently in a relational database. Second, integration with the broader analytic frameworks. So Labbit doesn't lock your data in. Customers are able to extract data from the graph if they're merging this into their own tools and own data lakes that they have. So this lets them incorporate the rich structured data from the graph into their broader AI models, dashboards, or even their own products. And lastly, graph federation. So some organizations are embarking upon this larger AI journey. And so for organizations that are already building graph-based knowledge platforms, Labbit can federate with those external graphs. This means there doesn't need to be a duplication of data. They can run cross-graph queries that combine lab-specific data with external ontologies or that enterprise-wide knowledge graph. And in closing, I did want to just say that just as the labs we work with are beginning to adopt AI to improve their operations, so is Labbit. So a couple of ways we're working to employ AI to make Labbit smarter, faster, and more valuable. First, we're streamlining configuration through use of a configuration assistant. So with this, users are able to upload process diagrams, SOPs, or requirements documents, or simply rely on the assistant's domain-trained knowledge, where Labbit will automatically then generate the underlying workflow and task configuration. So this is going to include not just the overall workflow and task structure, but all of those components that go into that configuration: inputs, outputs, task patterns, custom fields, even UI elements like data and queue grids. And so this is really is going to accelerate the onboarding and the configuration process for new lab workflows, as well as making updates to configuration. The second main area is really around unlocking insight from the graph database. Because we're sitting on this rich connected database, we're understanding how Labbit can best assist users to explore their data more naturally and also surface meaningful insights automatically without having to go in and look for them. Have this roll up to you as the user proactively. Great. I know we're running a little short on time, so I'm going to skip ahead, and I do want to say that I just want to extend a thank you to everyone for joining today's session. It's been really exciting to talk about the growing adoption of AI in laboratories, some of those real-world challenges that labs face in preparing for that future, as well as how graph databases and ontologies play this role in making data AI ready. If today's discussion sparked any ideas or questions on your side or around your own data journey, we really would welcome the opportunity to talk further and explore with you how we can support any of those needs.
Great job, Megan and Paul. You're right. We're right at the top of the hour. I think there was a question around, hey, we suffered with trying to implement LIMS for more than a couple years and scrapped it. What you showed today actually gives us hope in a process and an approach that we could actually be successful with. So that was the one. Any comments on that?
Yeah, absolutely. So that's not an uncommon story. I've worked in this industry a while, both as a consumer and on the vendor side, and it becomes common to see these lengthy LIMS implementations. That's one of the things that most impressed me about coming to Semaphore and working with Labbit is really on the implementation side because of the great team we have and also the configurability of the system. We're seeing these LIMS implementations last like under 3 months, if not sooner than that. So definitely reach out and love to chat further with you.
Yeah, that sounds great. All right. Well, thank you everybody for attending. This was a very informationally packed and a lot to learn here. And to hit that highlight again, we have clients that are super happy with the approach and the investment that they've made and how quickly they've gotten up and running. So keep that in mind and reach out to the Labbit folks if you have any questions or need help. So thanks, Paul. Thanks, Megan. And thanks everybody for your time. Have a great day and we'll see you next time.
Thank you, John.
Thank you.
Take care.
Bye.